very much for being here again. And now we continue with the second talk from our Uppsala connection. And Pietro is going to be with us only today and tomorrow. Then he has to fly back to Sweden. So he will tell us about the Quiver structure of knot invariants, open strings, and the recursion. So please, you have 1 hour.
Okay, thank you. Thank you very much, and thanks for organizing this once again and for the opportunity. So yeah, this is another talk about Chern-Simons theory, and it's based on joint works with Tobias Ekholm in Uppsala and Piotr Longhi, and also, so these were works from a few years ago, and I will tell you in the second half of the talk about some upcoming work with Tobias and the student Lucas Nakamura. So originally, these projects grew out of our attempts to understand a conjecture that relates two subjects in mathematics, knots and quivers, from the viewpoint of physics. So I'll start by reviewing our motivations and the goals that we set for ourselves, and then I will briefly review how the two sides of the conjecture arise in physics in the context of M-theory. In the third part of the talk, I will tell you about some of the new things that we learned from studying this conjecture. And in the last part, there will be roughly half of the talk actually, I will tell you about the new work and what we've learned recently about higher rank quantum curves and so-called scheme-valued quivers. So the knot-quiver correspondence is a statement, is a conjectural relation that is based on observations purely. And it says that if you take a symmetric quiver, which means you have a symmetric adhesion matrix, then, well, in the context of quiver representation theory, you can associate to such a quiver a partition function like this one, where the partition function depends on some formal variables. There is one for each node of the quiver. And besides being a series in those variables, this partition function is entirely encoded by Cij, the adhesion matrix.
Sorry, your matrix is symmetric.
It's symmetric.
Why do you have arrows?
They go back and forth. So, yeah, this is an unoriented quiver. Yeah. So, yeah. So the statement then is that anytime, well, so if you have such a symmetric quiver like this one, what you can do is you can take a specialization of the variables associated to the nodes to some powers of x, a, and q. And if you make this very specific choice and you reorganize this as a series in x, then the coefficients turn out to be certain types of knot invariants. So in this case, this would be reduced Hopf-Petit polynomials for the trefoil knot, colored by all symmetric partitions. So partitions with one row and n boxes. So that's an example of knot-quiver correspondence. There's many more examples. They were worked out for families of knots, including torus knots, twist knots, two-bridge, double twist, and so on. And in all these cases, which is infinitely many knots, we know that there is a quiver such that its partition function, once you specialize xi to some powers of a, q, and x, package in some way Hopf-Petit polynomials colored by symmetric partitions. Now, this kind of statement is a bit surprising, and it's interesting because as mathematical subjects, knots and quivers are very far apart, but of course we know in physics that they both arise in string theory or in quantum field theory. So, of course, knots and knot invariants like the Hopf come up in Chern-Simons theory, and quivers arise when describing, for instance, the world volume theory of d-branes. So then it's a natural question to ask whether we can use physics to say something about the knot-quiver correspondence, to understand where the quiver matrix or the variables ai and qi that you need to supply for the specialization, whether they can be explained in physics. You can go further and ask whether every knot has a dual quiver and whether the correspondence is a one-to-one correspondence. And also, you may wonder whether connecting knots and quivers in this surprising way, you may learn something new about the two physical settings where they come up. So you learn something new about physics. So let me remind you one place where knots come up in string theory. So given a knot in a three-sphere, one can define a three-manifold called the conormal Lagrangian, which is defined as follows. So you take S3, you think of S3 as the zero section in the cotangent of S3, and then along the knot, you can take a family of planes in the R3 fiber, which are orthogonal to the tangent vector. So you have a tangent vector along the knot, and you take the conormal plane. So that gives you a manifold which is topologically S1 times R2. You think of it as a solid torus. And that manifold intersects S3 exactly along the knot. Now, given this geometric setup, you can introduce the A model on T star S3 by putting n branes on the zero section. And then we know, since work of Witten, that open strings with both endpoints on S3 will give rise to a world volume theory, which is UN Chern-Simons. And likewise, if you take a single brane on L, you're going to get U1 Chern-Simons on L. And if you have both types of branes, then you will also have strings with endpoints on L and on S3. And so these will give rise to matter fields. So these will be bifundamental fields charged both under UN Chern-Simons on S3 and U1 Chern-Simons on L. And they will be localized at the intersection between the branes, so along the knot. Now, in old work of Oguri and Waffa, they figured out how to take into account these fields. They computed the one-loop determinant, and they showed that after integrating out the bifundamentals, what you get is an operator insertion in the path integral, which depends on the holonomies. So U will be the UN holonomy along the knot, and X will be the U1 holonomy of the theory on L along the zero section. Okay. Now, if you compute the expectation value of this operator insertion in the theory on S3, what you get is a generating series of Hom-Flippity polynomials, simply because taking trace in representation, symmetric representation n of the gauge holonomy on S3 as an expectation value gives, by definition, the Hom-Flippity. Okay, so this is how generating series of Hom-Flippity polynomials like the ones that we've seen in the knot-quiver correspondence arise in the context of string theory. And we're going to be interested in this setup in the Lagrangian limit. So it's been proposed by Gopakumar and Waffa that as n goes to infinity, the the open string topological A model on T star S3 transitions to closed strings on the resolved conifold. And pictorially, you can think of it as shrinking S3 to a point. And in the process, open strings can no longer have endpoints on S3, so they cap off, become closed strings. And one of the checks of this correspondence was the observation that the large n partition function of S3 Chern-Simons corresponds indeed to the closed string partition function on the resolved conifold. But we're going to be interested in this when we have an additional brane on the conormal Lagrangian. And so something similar will happen. So first of all, since this Lagrangian is topologically a solid torus, which intersects S3 along the circle, we can shift it off. It has a one-dimensional parameter space. It can be shifted off the zero section. When you do that, the world sheets of the bifundamental strings will stretch out and become annuli. And when you take the Lagrangian limit, these annuli, they cap off and they become open strings on the Lagrangian. So what you're left with after Lagrangian transition is a theory of open strings in the resolved conifold with boundaries on L. Okay? And Oguri and Waffa claim that the partition function of Hom-Flippity knot invariants coincides with the open string partition function of this conormal brane. Okay? So this is exactly the generating series that comes up in the not-quiver correspondence. And so we can take this as a starting point by reformulating this as a correspondence between topological strings and quivers instead of knots and quivers. So to take this viewpoint, we're going to start from the genus expansion, which says that when you take the string coupling to be small, the open string partition function is dominated to leading order by disk instantons. So the free energy is organized according to powers of GS, and the first contribution comes from genus 0. And we know, since, again, old work of Oguri, Wafala, Bastida, Marigno, that the disk potential can be organized according to a certain integral structure. Namely, it can be written as a series in dilogarithms where the coefficients are integer numbers, which are interpreted in M theory as counting M2 branes in given relative homology classes. Okay? So here I and J count the wrapping number of M2 branes on the P1 in the conifold, and J counts the wrapping number of the boundary of the disk inside L. Now, what's nice about the genus expansion, the leading order, is that when the string coupling is small, we can think of branes as geometric objects. So in particular, A branes can be thought of as special Lagrangian submanifolds with a flat abelian connection on them. And because of that, we can parameterize the moduli space of A branes by certain equations in C star times C star, where we think of X and Y as holonomies of the flat connection on the boundary torus complexified by the real moduli of the Lagrangian. And in this limit, then, the dynamics of this A brane will be described by local degrees of freedom. So these are strings which have endpoints on the Lagrangian, okay? And they give rise, so either to constant maps, which gives the Chern-Simons action, as in Witten story, but there can be also non-local ones. So when the string wraps a non-trivial cycle in the Lagrangian, and that's what gives rise to the disk instantons. So this is the low energy action in genus 0 for the brane. And if you want to find the quantum corrected moduli space, then you minimize this action. That leads to this kind of equation. And actually, the vacuum equation can be reformulated as an algebraic curve in C star times C star. So the statement is that this kind of curve, known as augmentation curve in symplectic geometry, what it does is it describes the moduli, the moduli space of the Lagrangian, taking into account corrections coming from genus 0 string instantons. Now, I said the nice thing about the limit of GS goes to 0 is the fact that we have a geometric description. We can think about the brane geometrically. And since we know that the open string partition function corresponds to a quiver partition function, you may ask, do we have a geometric interpretation of the quiver in this limit? So Q is e to the GS. We're going to take Q to 1. But to do that, in the quiver partition function, what you have to do is you have to take a scaling limit. So to get an interesting answer, at least, what we're going to do is we're going to take Q to 1, but Q to the D to be a variable Y. So then the sum, so D is the log of Y. The sum over D will be an integral in the logarithm of Y, in D log Y. And then the summand goes over to an integrand, which you can easily read off from here. So you're going to have dilogarithms coming from the denominators. So there's one dilog for each vertex of the quiver. There's a bilinear form in the logarithms of y's that's controlled by this pairing matrix, Cij. And then x to the d will give you log x, log y, some diagonal pairing. So that's what you get if you take the weak string coupling limit on the quiver partition function. And observe that we get this integral of some integrand, which I call W tilde. But because the not quiver correspondence agrees with the open string partition function, whose leading order was the disk potential, then you learn right away that this W tilde is nothing but the Legendre transform of the disk potential. Okay, so we'll see what that means in a second. So first of all, observe that the disk potential I told you was organized in some integral structure, but it features in general infinitely many dilogarithms. Whereas what's nice about W tilde is that we have only finitely many. There's one for each vertex of the quiver. Moreover, in W tilde, we also have certain quadratic terms in the logarithms, which are controlled by Cij. And we can think of these terms in a way that I'm going to make precise in a moment, as some kind of interactions among these dilogarithms. So I told you, dilogarithms, you should think of M2 branes. And then these interactions through the integral, what they do is they mediate the way that these finitely many M2 branes generate the entire spectrum that you see in the disk potential. So now, because the disk potential and W tilde are Legendre dual of each other, it means that their critical manifolds coincide, but the critical manifold of the disk potential was this polynomial called the augmentation variety. It's the moduli space of the Lagrangian. We learn that that moduli space can also be written in terms of the critical manifold of W tilde. And if you extremize W tilde, what you find is a set of equations like this. So there's one such equation for each vertex of the quiver. And the point is that these equations are extremely simple. They look like 1 minus y minus x, and then there's a correction next to xi, which is given by yj to the pairing matrix. Now, why are they nice? Well, because if you had a potential with a single M2 brane, then if you extremize this potential, you would get 1 minus y minus x. So that would be the moduli space of a single disk. So what we have in the case of the quiver is we have many such equations, one for each vertex. But now, if we know that each of them describes the moduli space of a disk, we can give an interpretation to the quiver itself. So the idea is that we have a number of basic disks corresponding to the nodes of the quiver. And these disks have some boundaries which lie inside the Lagrangian. So it's a solid torus. We have some boundaries going around. And we can think of the xi and the yi as the local holonomies of the Chern-Simons theory on the Lagrangian in the neighborhood of these boundaries. So xi is the longitude and yi is the meridian. And then what these equations are saying is that the disks are not just sitting by themselves, they talk to each other in a way that's encoded by Cij. But now, because xi and yi are holonomies, it follows that Cij must be the linking number between the boundaries of the disks. So if you have a red disk that winds around the blue disk, then its longitudinal holonomy will be corrected by the meridian, so yj, to the linking number. Okay? So that gives you a geometric interpretation of the quiver in the limit of weak string coupling. When we work at finite string coupling, though, the geometric description that I just gave you will be replaced by a quantum state in the Hilbert space of the Chern-Simons theory on L. And this quantum state can be described in terms of a wave function, which corresponds to the open string partition function. And it's a wave function in the sense that it's annihilated by an operator that's a Q difference operator that arises by quantizing the augmentation curve.
Just for given node, you can draw a quiver. Or not.
For many knots, you can.
For a node, who is it for a node?
For a knot, it's this. So the adjacency matrix would be 0, 0, 0, 1. Okay. This is for the unknot, unreduced. Unreduced only. The one who's, for example, so that H box is A minus A inverse over Q minus Q inverse in framing equal to 0. And there's a frame version. That's going to be this. and then you're going to have f here, f plus 1, and f, etc. So, but yeah, so for many knots, you can draw such quivers. There is a question whether you can always do it. We don't know. We don't know if you can always do that. And also the statement of the knot quiver correspondence is only about generating series of symmetrically colored Homfli-Petit. So we don't know if, in general, you can encode all Homfli-Petit in a quiver. Yes. 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 Yeah, well, definitely not, right? So we know, well, first of all, that quiver wouldn't be symmetric, right? And so for reasons that we just saw, that it encodes linking number, it needs to be symmetric. Also, we know that even among symmetric quivers, there's many examples that do not correspond to any knot. So it's an interesting question what they correspond to, and we can talk about it later, but the general consensus seems to be that there may be some three-manifold interpretation for some of these, even if they don't correspond to knots. But in general, it's not the case that if you take a random quiver, it will correspond to a knot. So for instance, I think if you take a two-node quiver, which does not have that linking structure, most likely it doesn't correspond to anything. Yes. Yes. Yeah, it works only for a specific ordering ambiguity. And one way to fix it is if you know what the generating series is, right? It fixes it for you. So that's one way to fix it, right? I mean, you want to get a quantum curve that corresponds to knot invariants. Knot invariants are given by whatever Chern-Simons on S3 or skein relations. But once you have those, it completely fixes this. There's other ways of getting this curve, which maybe we'll describe a bit later, but that also fix the ordering ambiguity. But yeah. Okay, so right. So what happens to the knot quiver correspondence at finite string coupling? So we're going to have a wave function. We're going to have an operator, Q difference operator, that annihilates. And in the quiver world, we can also think of the quiver partition function as a wave function. But remember, this is a function of many variables. So the Hilbert space will now correspond to a three-manifold which has many torus boundaries. And it will be defined by taking Chern-Simons on the solid torus, where we drill out small neighborhoods of the disk boundaries. So every time you drill out a disk boundary, you're left with a little hole in the solid torus. And then we're going to get a wave function on that Hilbert space. So wave function in the sense that we take the path integral, we define a quantum state, and we think of the quiver partition function as the wave function representation of that quantum state. And then the non-trivial statement is that such a wave function is again annihilated by a set of Q difference operators. So you can show that if you take any quiver, so this is true beyond the knot quiver correspondence, for any quiver it is true that it will be annihilated by all these operators, which are quantizations of the ones that we saw in the classical limit. And again, you have some ordering ambiguities that you have to fix, but once you have these, it's completely fixed. So what this means is that even at the quantum level, at finite string coupling, it's still true that quivers describe a finite set of M2 branes interacting with each other at all genera. Okay. Very good. So far I reviewed for you what was the interpretation of quivers in the context of topological strings. What I'm going to do next is I'm going to tell you a little bit about some new things that we learned from this interpretation. So remember I told you that the disk potential had an expansion into dilogarithms with integer coefficients, and that was a statement at genus 0, but it turns out that at all orders in the string coupling, there is a stronger version of this statement, which is that the open string partition function can be factorized into Q-Pochamer symbols with integer powers known as LM of E invariants. And once again, we can think of each one of these factors as contributions from M2 branes to the open string partition function. Now, I told you that quivers encode finitely many M2 branes, and somehow there's some interactions that generate the whole spectrum. But how does this work exactly? So there's a nice way to understand this mechanism. So the first step is to switch from functions to operators, where we take a QPOCammer and we replace it with an operator in a quantum torus algebra. So X hat is a quantum torus operator. And then what we're going to do is we're going to correct these holonomy operators, these are the longitudes, by taking into account the linking numbers among the disks. So I'm going to define some new variables, capital X, which is the small x times yj to the Cij. And the moment I do that, these holonomies do not commute any longer. Okay? Then the non-trivial observation is that it turns out that if you take one contribution for each node of the quiver, so you write finitely many QPOCammer symbols, but now with these quantum torus variables, and you write them next to each other, you take normal ordering, which means you push all the y operators to the right and pick up powers of q, then this very simple expression actually gives you the quiver partition function. So in the not quiver correspondence, you know that PQ is equal to Z open. Z open is known to have this infinite factorization. But when written in operator form, you have a finite product, finitely many terms that talk to each other through this quantum torus algebra. So one striking thing about this observation is that there's integrality, LMOV integrality, so these numbers counting M2 branes, which is respected by the quantum torus algebra, right? So because here everything has integer powers, and here as well, in fact, all the powers are 1. But what this suggests is that not only you have an algebra of quantum torus variables, the usual one, but you should also have some algebra of these QPOCammers that somehow respect the integral structure. And the idea is that whenever you have two disks that link each other in this way, you might be able to unlink them like we do here, but you have to be careful. The price you would have to pay is to add the bound state. So there's some kind of skein relation that would be literally true for X and Y. But when we play this game at this level, it's a bit non-trivial because the QPOCammer includes all the multiple covers of our curves. So nevertheless, we can postulate this thing. And if we believe this, then it would mean that there should be an equivalence between a quiver with 2 disks and 1 unit of linking, and a quiver with 3 disks, where the third one self-links, and it's going to be the bound state of the other 2. So that's indeed true. This prediction works. If you set x3 to be q inverse x1, x2, then you can show that thanks to this identity, it turns out that the quiver partition functions of these quivers actually coincide. In fact, this kind of identity is very familiar. It's just an instance of the pentagon identity of Fadeev and Kashaev, which says that you can either write down a product of 2 QPOCammers or 3 QPOCammers, but the catch is that you have to do it precisely with this kind of quantum torus variables. Now, the point is that this operation was predicted geometrically, and in the same way, you can predict many new identities. So now we have a statement purely at the mathematical level, again, beyond the context of knot theory, that whenever you have a quiver, it's going to be a symmetric quiver, you can always remove a unit of linking between any pair of nodes and create a new quiver where you have a new node, which is the bound state of the 2 that you unlinked, and the new node is going to link with everybody else in a way that is dictated by geometry, okay? And this operation can be used to start from a small quiver and generate a bigger and bigger quiver. So you can generate the whole spectrum of LMOV invariants starting from the finite set of basic nodes in this way. So to summarize, what we learned so far is that the not-quiver correspondence is definitely not one-to-one, right? I just told you there's a set of dualities that gives you infinite numbers of quivers, all having the same partition function. But it is true that there's minimal choices. So for every knot, there seems to be a quiver which has a minimal number of nodes that encode everything else. I also want to briefly mention that there's a statement in quantum field theory of this kind of relation that comes from the 3D correspondence. So I told you that these quivers are describing the geometry of certain three manifolds, some Lagrangian manifolds. And you can associate to these three manifolds some 3D n=2 quantum field theories called T of Q, for which we have an explicit Lagrangian description. And these are dual to these geometries in the sense that the vortex partition function coincides exactly with the quiver partition function. But then if that is the case, these kind of operations describe two different types of theories, so with different gauge groups and different matter content and Chern-Simons couplings and so on. And the statement that quiver partition functions coincide then says that there's a duality between these theories, or at least at the level of vortex partition functions, you have two different theories with the same partition function. In fact, it turns out that this kind of dualities can be understood in QFT as combinations of known dualities, such as particle vortex and SQED XYZ. So in a way, we recover some known but fairly non-trivial statements at the level of QFT, and that provides some nice consistency check for this story in the topological string context. Very good. Maybe I'll pause if there's any other questions. No? Okay. Okay, so now we get to the new part, which is the story of high-rank quantum curves. So let's go back to the original setup of Oguri and Vafa. So again, we consider T star S3. And in T star S3, we're going to take conormal Lagrangian, L, which intersects the zero section along the node. But now we're going to modify the setup a little bit by taking not just one brane on L, but a stack of branes. And of course, what that is going to do is it's going to give you a non-abelian theory on the Lagrangian. You're going to have UM Chern-Simons. Now, once again, we're going to take the large N limit. So we're going to shrink away the S3 and transition to the resolved conifold. And in that limit, what we're going to get is, again, the open string in the resolved conifold. But now the open string partition function will be a sum over all partitions. So we're going to have home flippy T polynomials colored by arbitrary partitions with up to m rows. Okay. Then one can ask, okay, so how much of the structure that we found in the context of symmetric partitions survives, right? For example, is it still the case that home flippy T polynomials with arbitrary partitions are generated by Quiver, right? What happens to the basic disks and the interactions at their boundaries? And do we have some analog of the quantum curve, some recursion relation that we had for the generating series of symmetric home flippy T polynomials? Do we have something like that for arbitrary partitions? Now, there's a big difficulty from the physics viewpoint with dealing with this generalization, which is the fact that we have to deal with complex non-abelian Chern-Simons. So defining the Hilbert space for complex Chern-Simons for higher rank gauge group is notoriously subtle. And also describing the algebra of observables is something that hasn't been done except for very special cases. So to sidestep this difficulty, what we're going to do is we're going to make some working assumptions. And we're going to make two assumptions, later supported by checks. The first assumption is that we're going to model the Hilbert space of complex Chern-Simons on the solid torus by the scheme module of the solid torus. So what does that mean? It means we take a vector space where any vector corresponds to a configuration of lines like this one. So whenever you have the solid torus with ends identified, you think of this configuration as a vector modulo certain equivalence relations known as the Hom-Flippity scheme relations. Okay? So they're not all independent, but they come with some equivalence classes. Now, one nice thing about the scheme of the solid torus is that it's been studied extensively by Morton and collaborators. And in fact, there's even a very nice basis for this vector space, which is labeled by a pair of partitions, lambda mu bar, which in physics is nothing but the Verlinde basis. It's some generalization of the Verlinde basis to infinite rank Chern-Simons. Okay? So Verlinde basis, for those who might have forgotten, is when you take the solid torus, you take a Wilson line in representation lambda along the core of the torus, and you just compute the Chern-Simons path integral and get a state on the boundary. That's what this basis is doing. Okay? Except that these lines, when people talk about scheme modules, they're just fundamental Wilson lines. Okay? The second assumption we're going to make is that we can model the algebra of observables of this theory by the Skene algebra of the boundary torus. So on the boundary torus, you can define some operators, like the meridian operator or the longitude operator. And whenever these operators, so this will be labeled by some homology classes whenever these homology classes are primitive, so the Pij with Ij coprime, then these correspond in fact to Wilson lines in the fundamental. And in any case, we know that the algebra of these observables is given by this simple relation, and it acts on the solid torus that's going to be inside just by stacking this thickened torus onto the solid torus. So then you include the lines and you get some new element in the scheme. Okay? So once again, the reason why it's nice to work with this is that it's known explicitly how these operators act on the scheme module. So for example, the longitude just adds boxes in all possible ways, and the meridian is diagonalized in the Verlinde basis. Okay? Okay, very good. So we're going to start again with this Oguri-Vafa setup, where now we have many branes. And we can then think of the Hilbert space of the not conormal Lagrangian as the Skene module of the torus. And if we do that, we can view the quantum state of Chern-Simons theory on the Lagrangian just as an element in the Skene. And if we work in this Verlinde basis, then we say that the vector that we get is given with coefficients corresponding exactly to the Hom-Flippity polynomial. So we say that we know what is the vector in this vector space. We just define it in the Verlinde basis using the Hom-Flippities. Okay? And then what we'd like to do is we'd like to study the structure of this state. So we want to understand whether it can be described by some kind of quiver, like we did for the partition function earlier, and whether it describes, whether it's annihilated by some kind of recursion relation, like A hat. So to warm up with this new formalism, let's take a very simple example. So in general, you may say, okay, if we know that something in the abelian setting is annihilated by A hat, which is a polynomial in x and y, why not just replace x and y with P01 and P10? That's a naive way of proceeding. And it works beautifully in simple cases. So for example, when you have only one basic disk, as we said before, the partition function is a Q-pochamer. And the Q-pochamer is annihilated by 1 minus y minus x. So if you take these statements and you lift them to arbitrary rank, then the Q-pochamer uplifts to this linear combination of Verlinde basis states. This is nothing but the topological vertex with a stack of branes on one of the legs. And the statement then is that this is annihilated by this triple of operators, P00, P10, P01 for 1 minus y minus x. Okay? So it works very nicely, but it only works in very, very simple cases. Okay? So examples of things that can go wrong, for instance, is that you know that you have ambiguities that Alba was mentioning. When you present operators in x and y, you can always swap them at the cost of introducing some powers of q. That's not true in the skein. P10, P01, they have a non-trivial commutator. They don't just q commute. And also, well, when you have quantum curves like a hat, you can left multiply by anything you want. It's still going to annihilate, but it turns out that if you try and do that in the skein, the answers you get are not so simple. So as a general rule, the higher rank theory turns out to be much more rigid than the U1 theory. It's not so easy to compute these operators beyond very simple examples. So to find structures in higher rank not invariants, you need some new ideas. And what we decided to do was to resort to some geometric package called knot contact homology. I'm going to briefly say what this is. So the idea is that we had this classical curve, the augmentation curve, that was the moduli space of the brane. And there's a way of thinking about this curve in terms of geometric data at infinity. So what does that mean? So we have the resolved conifold X with a Lagrangian that is non-compact. It's a solid torus with boundary at infinity. And if we look close to the boundary of the geometry, X and L approach are the radial direction times a contact manifold Y, which is the unit cotangent of S3, and a Legendrian torus lambda. So lambda is just the torus at the boundary of L. Okay. And then if you do string theory in this context of a manifold with boundary, in addition to the strings with finite area inside the bulk, you can also have holomorphic curves that will run to infinity. They will have some infinite sort of world sheet. But you see, if they run to infinity, the radial direction is paired by the complex structure to the Reeb vector field in the contact boundary. So there's a vector field in the contact manifold Y. And the statement is that if a string goes to infinity, it must do so in a way that it approaches a flow line of this Reeb vector field. So you can have world sheets like this, which are open strings with boundaries on some Lagrangians inside, and then at infinity they approach some Reeb chords which end on the Legendrian. Now, physically, what does that mean? Why is it a natural thing? Well, it turns out that Reeb chords, so flow lines of the Reeb vector field, are in fact the critical points or the minima of the string action. Okay? So in other words, they generate the space of classical vacuum at infinity. So if you have a string, which is to have some boundaries on a Legendrian at infinity, you want the string to have minimal energy, minimal length. And that's exactly achieved by the Reeb chords. So you have a finite number of such chords which correspond to the classical vacuum states of your strings at infinity. So once you classify your Reeb chords, you can use them to write down the vector space of vacuum. It's going to be graded by how many boundaries, how many Reeb chord boundaries you have. And then in each sector, you're going to have strings with a certain number of boundaries on each chord. And then at the quantum level, this classical vacuum will be destabilized by instanton effects. So what happens is that you can have world sheet instantons that transition between a certain vacuum state. So there will be some collection of Reeb chords going to some other collection. And so you can define a map defined by the instantons from this vector space to itself. And So this map just takes, as I said, some linear combination of rate chords to some other linear combination, and it turns out that this map is nilpotent. So it defines a differential on the vacuum space of states. So the space of true vacua then, corrected by these instanton effects, would be the cohomology with respect to this differential. So this would be the truly stable ground states of strings at infinity. So let me try and illustrate how this works with a very simple example. So again, we take the toric brane in C3, and the toric brane is a solid torus. Here we're looking at the torus at infinity, so the boundary of the toric brane. And we have a single Rabe chord C, which has two boundaries, C plus and C minus, the endpoints on the Legendrian torus. Then we need to compute this differential, which means that we need to compute all holomorphic disk instantons that act on the space of vacua generated by this single Rabe chord. And it turns out there's three disks. So here I draw the projection of these three disks on the torus at infinity. And what you can do with this then is you can say, okay, let's now cap off the Rabe chord at infinity by some choice of line. So we're going to choose the inverse of P00. And you see that if you do that, then when you cap off this disk, you're going to get something contractible. But when you cap off this one and this one, you're going to get something that looks like the longitude and the meridian. And so the collection of these three curves gives you an operator that is exactly the recursion relation that we guessed earlier. So this is a derivation from infinity of that recursion relation. Yes?
So can I ask something trivial? Because what was
yes.
I don't understand how you out of Cavalier you make something line times contact manifold. So what are you doing?
Yeah, there's some operation called stretching of the complex structure.
Which parameter you're stretching?
So there's a stretching of the complex structure at infinity.
So what do you do with S3? In which sense you identify C3 is contact manifold times line?
Well, so yeah, I don't think I should go too much into details. But the idea is, right, so you want to stretch the symplectic structure near the contact boundary. So you want to...
But what's the contact boundary? So we have a theoretical ideals, which we all understand.
No, but any symplectic manifold with boundary, right, locally near the boundary is contact. Yeah, that's the only statement, right?
But then what do you do?
Well, then we just look at that. I mean, so what we need, so the kind of information we need.
So you take a Cavalier, you look at infinity, it's
yeah.
contact manifold, and
yeah.
then you just forget everything, you take this contact manifold times line and you do contact homology.
So, well, that's a correct statement. So the only thing you need to know is how your Lagrangian ends at infinity. So you need that information about the Legendrian inside the contact manifold.
And the rest is irrelevant. So you can read all the information.
So, well, okay, it's not entirely relevant. So there's some technical details, which, yeah, I don't know if I should get it, but so there's some information, for example, about something called 4-chain, right? So, for example, if we're in T star S3, we have this S3, which is a zero section, and when we count curves even at infinity, we want to keep track of how much they wind around S3, right? Or how much they wind on the P1 in the conifold. And, well, consistent way to do that is to introduce some kind of, well, some people call it a Dirac string, but it's more like a flux tube, which is a 4-chain whose boundary is S3, but then it goes to infinity in a certain way. So you need to keep track of some additional information, but it's very, very mild topological information in that sense. Otherwise, really all you need is the contact structure. You need to know what is the Rabe vector field, and that's all you need to draw these pictures. So here the only information from the contact structure is the fact that there's a single Rabe chord.
Physically motivation.
Oh, so yeah, so physically the motivation is, what I tried to sketch is the fact that you have like in Chern-Simons theory, right? When you want to discuss what is the Hilbert space, you look at the boundary of your three manifold. So here it's the same. You have a Calabi-Yau with a brane inside, and you want to look at well, some notion of ground states for the open strings in this setting. And it turns out that the ground states, by definition, are the Rabe chords, right? Just because they're minima of the string action functional. Now, this setup, it really comes from math, so it was not motivated physically initially, but another motivation comes a posteriori. These people in mathematics, they showed that studying this contact structure at infinity, you can derive moduli spaces of branes in this way. So they can describe augmentation varieties like A polynomials and augmentation polynomials and so on, including the higher genus version. So and yeah, this has a physical interpretation, but we shouldn't get too much into that. Yeah. So but the idea is again that now we're trying to do the higher rank version of that, where we go beyond Homfly PT polynomials colored by symmetric partitions. We want to do it for all partitions. And the question we're asking is, how do we get a quantum curve? How do we get some recursion relation for that? You cannot just guess it. It's very hard to guess it, even if you know what the partition function is. So we're using this geometric framework to see what happens at infinity and derive the quantum curve, but some Skane valued version that works at all ranks. Okay, let me try to speed up a bit and wrap up. So yeah, so this example shows you how looking at this geometric structure at infinity, you can actually derive the operator that we guessed earlier for this very simple example. Now, why does it work? Well, because I told you that the way that we build this is we take the differential acting on the Rabe chord, so that's something in the image of the differential, and then we cap it off. So since this is in the image, it must be trivial in cohomology, it must be 0. And so what it does is it defines a quotient of the Skane algebra. It's called the Skane D module. You start with the Skane algebra of the solid torus generated by these operators, and you take a quotient where you say that a certain linear combination of these things is 0. Okay? It's an analog of a D module, but in the Skane. And then from that point of view, the Chern-Simons state on the brane, so the partition function of Homfly polynomials, is just a homomorphism from the Skane D module to the Skane of the solid torus. Again, what does that mean? It means that it's a map that maps A, so this operator that's 0 in the D module, it maps it to an element of the Skane, which is 0, right? That's why it's a homomorphism. It maps 0 to 0. So that's the statement of the recursion relation in the Skane. And that's the kind of thing we want to build more generally. Now, there's many things that can go wrong. So even this example is a bit too simple. In general, what happens is that, these disks that I've shown to you, it's not always the case that you just have positive Rabe chords. Sometimes they really interpolate from some vacua upstairs and vacua downstairs. And when that is the case, well, you cannot just cap it off. You have to work your way through the equations and do some elimination theory. You have to get rid of outstanding Rabe chords to get some nice equations. And in general, so we looked at a few examples. In general, it's not clear you can always do it. We don't know whether it's possible or it's not possible. It's a bit of an open question. But when the answer exists, it's essentially unique. It's an extremely rigid problem in contrast to what we know in the U1 setting. So the main example that I'm going to discuss very briefly is that of the Hopf link. So that's the Hopf link in S3, the negative Hopf. You can build it by taking two toric branes in the resolved conifold. And then the partition function, or the quantum state of Chern-Simons theory, will be given by this generating series of Homfly PT polynomials colored by arbitrary partitions on each of the branes. Okay. So if you take the Hopf link and you look at infinity, you look at the rate chords and the flow lines and so on, then you can compute your differential using these kind of pictures. You can compute it explicitly. And so there's a rate chord here called C11 that has both endpoints on the first brane. There's another rate chord called C22 with both endpoints on the second brane. There's more rate chords, but we're not going to worry about those. The point is that if you compute your differential, you find that the boundary of C11 features now 4 disks plus a 5th disk with 3 punctures, 3 boundary rate chords. And that's exactly the kind of problematic guy that you have to somehow get rid of if you want to get some nice operator equation. Now, in this example, you realize that if you do the same computation for C22, actually a very similar disk comes up in the differential. And in fact, it turns out that you can choose a capping path for this guy so that alpha 1, gamma 1, alpha 3 matches beta 2. So that's what's written here. And vice versa, you can cap this guy with gamma 2 so that this piece of the boundary on brane 2 matches alpha 2. Okay? So these some equations you can write down. You do your elimination theory, and after you choose this very special choice of capping path, which you see is unique, there's no messing around with that, then you get a well-defined operator that's written entirely in terms of these closed Wilson loops on the Lagrangian. And the statement is that it is this operator that will annihilate the partition function. But that's not enough. For the Hopf link, you need, it turns out, 3 operators. So you can compute some more by studying the cohomology of the differential. But then the statement is that these 3 operators completely determine the partition function. So there's a unique solution to this recursion relation that gives you the generating series of Hom-Flippity polynomials for the conormal filling. You can also move branes around and get some more interesting fillings, and these fix everything. Okay, very briefly, there's a quiver structure in this partition function. And what it says is that the whole generating series of Hom-Flippity polynomials is generated by 2 disks on the first brane, 2 disks on the second brane, and then there's 2 annuli that link the disks in the way that is shown here. And you can write down the generating series of Hom-Flippity polynomials of the Hopf, again, as a product of finitely many curves. So basically 1 curve for each disk and each annulus, with some twisted products, which I'm not going to explain. Okay, so to summarize, we learned that quivers organize open string partition functions into finitely many M2 brane contributions, talking to each other by linking. There is a new type of skein relation that we call the multiple cover skein relation that explains how different M2 branes talk to each other and how they generate the entire spectrum of LMOV invariants. And when you have multiple branes on a Lagrangian, then you get that open strings compute knot invariants covered by arbitrary partitions, and usual recursion relations can be sometimes lifted to skein-valued recursion relations. And for the Hopf, we obtain this. We define skein module. It computes Hom-Flippity covered by arbitrary partitions. And we also see that a quiver structure continues to exist in higher rank. So I'll stop here.
Is there some relation of this structure with the symplectic theory by Pietro?
Yes. So symplectic field theory is this bigger or more general package. So yeah, I don't want to say too much, but the point is, symplectic field theory has some applications to Legendrian contact homology, and then Legendrian contact homology is a more general version of this knot contact homology. So there's some specializations to go through, but this is exactly that. right? So in Legendrian contact homology, yeah, you have a way of building a DGA associated to a Legendrian that's generated by the Rabe chords and by the holomorphic disks that interpolate between Rabe chords. It's exactly that. Yes. It's just that it's applied to.
More explicit.
Absolutely. Yeah.
There is just formal construction.
Yes. So this is just an application. So and it works. So the general setting, of course, applies to any contact manifold and any Legendrian, right? So here we're just looking at it in the very special context of the conifold with not conormal Lagranges. Actually, I keep talking about not conormal, but one of the things that one can do, and it's interesting to do, is to explore the entire moduli space of Lagrangians. So the philosophy, since you're asking about Legendrian contact homology and symplectic field theory, the philosophy there, which I think we should try and bring a little bit into the way we think about branes, at least in the topological A model, is that you really start from infinity. So at infinity, you have a contact boundary and you have a Legendrian there. And what mathematicians like to do is to ask the question of what different ways exist of filling the contact boundary and the contact Legendrian with the Lagrangian inside. So for certain types of filling, you may get a not conormal, but then there's other types of filling, which in physics we think of as moving the brane on different legs. But then you find out that this topological vertex picture doesn't quite exhaust all the things that can happen to your brane. For example, there can be fillings where branes merge together and recombine into a single brane, which in physics you would have to add in by hand and saying that there is a complement filling, like when you take the Hopf link and you look at it in the complement of S3. But it doesn't come from the vertex, right? In the vertex, you always have two Lagrangians. In mathematics, all these things are in the same moduli space. They're all computed as different Lagrangian fillings of a Legendrian at infinity. So it's a very powerful picture. I think it's conceptually. Yeah.
There is a strong connection with integrable systems, no? Because you have described the Hamiltonian flow
Yes.
in this R direction.
Yes.
So do you see some integrability, some connection with
I don't know. There's probably many, but depends where you look, right? There's some, yeah.
whether these partition functions can be related to some integrable system, for example, Quivers?
Well,
These are defect partition functions, right? I mean,
these are
you have
defects.
these
Yes.
five
Yes. Yeah.
graphing, this
Yes.
is Lagrange, so they are 3D
Y-
in
y-
codimension 2 and 5D,
That's right.
or in 4D.
Yes.
So you will have a kind of defect partition function in 4D gauge theory.
Yes.
in some
Yes.
sense.
Absolutely. Yeah. If you go down to type 2A, you're going to have a 2D 4D system. Yes. Exactly. Or
Is
3D
there any
5D.
interpretation of this in that framework?
Well,
Structures?
yeah, of course. I mean, there's this whole story of topological strings and integrable hierarchies going back to early 2000s. So observations that you have W algebra type constraints, Virasoro constraints, and these partition functions. I mean, there's that connection, for example, but I think that's actually not the only one, right? So I really don't know which angle to take on your question. I think there's more than one connection to integrability. Yeah, but yeah, Maxime.
So I have elementary question because I still don't understand. So you take a toric material,
Yes.
you go to infinity, you have a contact manifold,
Yeah.
forget about brain, but then you will have this contact homology,
Yes.
right?
Yeah.
What's the physical interpretation of this thing?
So
Is it the same?
yeah, there is
Even without brains, because
without brain. Oh, I see.
I mean, there is you're going for much more complicated
Yeah.
homology, but I'm asking,
Right.
take without brains. I mean, what are RIP guys?
Yeah. Okay. So
Differential on
yeah.
this,
Yeah.
so-
Okay. So if you do literally this without brains, it's kind of interesting because well, so you just have the resolved conifold, right? And then the analogous question, like what is the DGA at infinity and what is the complex? Well, I told you you have to look at vacuum states. So now this will not be generated by Reb chords because Reb chords end on branes. You have no branes. It will be generated by Reb flow lines. So you look at closed loops, right? Turns out that for the resolved conifold, there's none. Why is there none? Well, physically, you could interpret this as the statement that when you take large n, you create some kind of black hole, and there's no strings that can go out from the black hole all the way to infinity. I told you that these flow lines, these Reb flow lines, they are asymptotic boundaries of holomorphic worldsheets that escape all the way to infinity. So in that case, the story is kind of simple, right? There's just yes. If you go to another yeah, that's right. But then yeah, then it gets a bit tricky, right? Because then we're talking about geometric transitions for things like length spaces or other orbifolds. So in that case, there is non-trivial Rave flow lines. And it's a bit of a puzzle physically what they mean, right? Because you wouldn't expect that thing. Yeah, yeah. Okay. Yeah. No, it's no, it's open. It's open. Yes. Polynomials that depend on. Yeah, okay. I think I understand. This one? Oh, I see. When you have only two variables. Yeah, no, in that, so you mean a single node quiver then? We just have x and y. Yeah, no, in that case, it's just y minus x, and then minus, well, there's some power of q, and then y to the f equal to 0. So it's a framed toric brane, basically. Yeah. Yeah, this is just the T transformation on that. Yeah, F times. Yeah, so in the simplest case, it's just a frame toric brane. But then again, that's in line exactly with this observation that the way you should think about the story of quivers is that you take some complicated Lagrangian that looks very fancy, it self-links in some funny way when it intersects the zero section, but out somewhere else, this Lagrangian inside looks like many copies of the toric brane. So there's some disk boundaries, and in the neighborhood of each of them, you have one of these things. So this describes a little toric brane, and then they're glued together in a way that's described by the linking matrix. Yes, of course. Yeah, that's exactly the point. So yeah, I didn't say this, but the point is that so in the classical story, maybe I'll return this one. There, yeah, okay. Okay. So both in the classical and in the U1 quantum story, what you do is you have to specialize xi to be some -1 to the cii, and then some x a to the ai, q to the qi for some integers. So these are valued in z. And you have to say that y is the product of all yi, right? Is it clear why this is the case? It's because, so if you think about your solid torus with many kind of Wilson lines inside, then the yi are the little holonomies around each of them, and the big Y is the overall holonomy. So this just says that the overall holonomy is the sum of all of them, okay? And then the statement is that once you take into account these specializations, then you can do elimination theory on this set of equations, and what you get is exactly a of x, y equal to 0. So you get some non-trivial equation in this way. So, like basic example was this unknot, right? So for the unknot, if you have two nodes, you have 1 minus y1 minus x1 equal to 0, 1 minus y2. I'm going to do the classical version, but you can do it at the quantum level. It's x2, y2 equal to 0. And then if you apply these things, you get 1 minus y minus x plus a square xy equal to 0, which is very easy to see because, y1 is 1 minus x1, y2 is 1 over 1 minus x2. And when you take the product of these things, you get 1 minus x1 over 1 minus x2. But x1 is x, x2 is x times a square, and so that's exactly this equation here.
And that is the Seiberg-Witten curve?
Well, yeah, you can call it the Seiberg-Witten curve of the resolved conifold. It's Seiberg-Witten curve.
Right.
Yeah. So one of the things that emerged from this story in a paper from 2013 of Nina, Kumrun, and Tobias and Lenny is that what people call the mirror curve is just a moduli space of the toric brane. But you can take the same Calabi-Yau, go to another brane, so you take a more complicated brane, you're going to have another moduli space. And in the open strings, it describes a different partition function. The closed string, it should contain the same information. It's just another mirror for the conifold. So it's a Seiberg-Witten curve. Okay. You mean some non-trivial Four cycle. So yes and no, in the sense that some of these curves appear to be some degenerate limits of curves with internal points. Okay, so with non-trivial, yeah. But at the end of the day, they should all be mirrors to the conifold. So there's only one modulus, which is the conifold modulus, right? There's nothing else. But this is something that hasn't been explored very much. So yeah, it's all based on expectations.
And these set of equations, they admit isolated vacuum also, or
so
also families, just like.
You mean when you solve y as a function of x?
Right.
Yeah, these are polynomials, so they're all isolated vacua. Yeah. Of course, there are some points where vacua converge, and you have branch points and so on.
But generically, it's isolated, just some points.
Yes, it's just some points. Yes, because as you said, this is a 3D 5D system. In the 3D theory, you have some twisted superpotential. You minimize, and you get some massive vacua, which are isolated. Yes. Mm-hmm.
They correspond to some anions in this 3D theory, or what?
So the vacua correspond to, so you have a spectrum of BPS states, right? They correspond to vortices. So in each vacuum, yes, you have some vortices. So more precise.
Inside the torus and on the boundary.
Yeah, well, okay, so more precisely, what you do in general, right? You're going to have some equation like a of xy equal to 0. When you solve this, you have a bunch of solutions, yi of x equal to some functions, right? And there's one of them that's distinguished. So let's call it I equal to 1, such that y1 goes to 1 when x goes to 0, okay? Then for this very distinguished vacuum, you have that the partition function there goes like e to the 1 over gs times w disk. And for this partition function, for this vacuum, this corresponds to the vortex partition function of the 3D theory. There's other vacua which have similar behavior but slightly different interpretation. Yeah. Okay. Thank you.